with that, today I'm going to pass it off to Felix. Felix is actually one of the drivers behind CMSIS-NN, the library that is critical for getting optimized performance from the Cortex-M processors that you've been using. So Felix will talk about what TFLM, in fact, like TensorFlow like Micro uses. But CMSIS-NN is not just dedicated for TensorFlow like Micro. It happens to use it. Many other systems also rely on CMSIS-NN, so he'll talk to us about that. Pete, would you like to add something about Felix and the CMSIS-NN?
Yeah, I definitely. I mean, the work that Felix and his team are doing is really absolutely crucial to TF Lite Micro. We rely entirely on their work to get optimized performance on ARM Cortex-M microcontrollers, which are like 90% at least of the 32-bit microcontroller market. And it was a bit scary at the start, sort of saying, hey, we're actually going to outsource all of the optimization work to somebody, to a team at another company, and rely on sort of just, Google internal products rely on this. So it was kind of a big, scary thing to do. But it's been absolutely fantastic working with Felix and his team. They've been doing amazing work to speed up running ML models on these devices. And like you said, it goes beyond TF Lite Micro. But for us, it's been really an amazing experience, and we're so grateful to have Felix and his team doing this work. I really can't rave enough about how nice it's been to just see the improvements that have come from the work that Felix and his team have been doing.
Awesome. So thank you, Felix, for making the time. I really appreciate you making the time and putting all the content together and stuff. So very much looking forward to what you're going to teach the students. So before we turn it over to you, I'm curious, you say outside of work, you're an active music photographer. What does that mean? Or is that a typo?
No, it isn't a typo. So I photograph concerts for a couple of music magazines here in Sweden. So I visit music festivals and regular concerts and photograph with other photographers.
Cool.
So right now it hasn't been much of that.
I wonder why. You can just get online, play a YouTube concert. It's like what my kid does. Totally has a nature show going on. And then while the nature show is going on, I'm often like, get out and do something. And I'll go take nice pictures. She'll put a nature show on and then take pictures from the nature show. It's pretty amazing. I'm like, why would you just not get out? And she's like, I can get much better pictures on the TV. So,
yeah.
All right. So I just stopped sharing screen. You should be able to.
Yeah, I gave him access, I think.
Okay, awesome. So Felix, you can share a screen.
All right. Thanks, Pete, for those kind words. And thanks for the introduction, Vijay.
Sure thing.
So let's get started now. Do you see my screen now?
Yeah.
Cool. So thanks, everyone, for joining us today. I'm Felix. I'm part of ARM's machine learning engineering team based in Lund, Sweden. I work primarily with optimizing machine learning kernels for Cortex-M CPUs and on the story around it. And in today's session, we'll go through what CMSIS-NN does and about library optimizations in general. So this is a rough itinerary of what we have planned today. The first two bullets are a quick introduction to CMSIS and how it relates to TensorFlow Lite Micro. And then we take the important question of why do we need to optimize for TinyML before settling on to the main topic for today, which is optimization. We'll unroll the topic into smaller sections as we progress. So the Cortex microcontroller software interface standard is a collection of API definitions, libraries, utilities, and methods that simplify and accelerate the creation of microcontroller applications. CMSIS is provided by ARM with a permissive Apache 2.0 license, and the software components can be used by open source and commercial projects. Now, the DSP and code libraries have been around for a while, and the NN library is a relatively new addition. It's just 2 years old. And I'm also the maintainer for the CMSIS-NN library module. Right? So how does CMSIS-NN relate to TensorFlow Lite for microcontrollers? What CMSIS-NN provides is optimization for a subset of compute-intensive operators that are in the TFLU repository. And the support is only for int8 kernels. The way that you access it is through TensorFlow Lite Micro. And if TensorFlow Lite Micro's interpreter sees an optimized kernel available, then it uses that. If it doesn't, then it falls back on the reference implementation. The advantage that you have here is that as long as your network has operators that are supported by TensorFlow Lite Micro, you'll be able to run them. And optimization is something that you can gradually add on to it. Right?
Can I ask a quick question here for students?
Yeah.
So when you're thinking about like the operator, the optimization support that some general package like CMSIS-NN would provide, how do you go about picking what ones to optimize? Because Pete had previously mentioned that, look, we don't take all the operators, right? We don't implement all the operators that are coming in. So in a similar vein, is the goal here for CMSIS-NN to, well, if a framework like TF-Lite Micro supports it, then okay, we'll provide all the necessary optimizations, or is there some way you would even distill that?
We look at the models that are popular in the field currently, and then we look at the operators that consume the most cycles in those operators, in those networks, and decide the operators that we pick from the wider subset. Does that make sense?
Yeah.
So now, why do we optimize for TinyML? Of the multiple reasons, if I have to pick 2 reasons, I would pick power constraints and cycle constraints. With optimization, what you essentially do is you reduce the awake time of your edge device and thereby extending your battery life. Just that is a very powerful motivation to optimize for TinyML. And on the cycle constraint aspect of it, it allows you to use more complex models within the same inference budget. And it also, if you have real-time constraints, it helps you to achieve that as well. So those are the top 2 reasons that I would consider on why you should optimize for TinyML. So whose responsibility is optimization? As it is easy to dismiss optimization as something that is beyond me, or it isn't my problem. But as the proverb goes, it takes a village to raise a child. I believe that everyone has a role to play in optimization, some more important than the other. In this section, we'll not be discussing the hardware design aspects, as most of the hardware design aspects related to optimization is quite similar to the optimization aspects that are involved in NPU design. That is something which my colleague Thomas will take up in the next session. So the focus today will be on the other 3 aspects, which is model, software environment, and library optimization. All right. Now let's get into the details. We'll take the first part, which is the software environment settings. Now, as boring as it may sound, it is the foundation on which optimizations are based on. It is also the moonwalking bear in projects. The different levels of this pyramid are all related to compiler options, and some have its own level to signify importance in the bigger picture. And when using libraries and projects picked up from multiple sources, it is easy to underestimate the source of the issue and chase after non-existent issue. That is why you have the iceberg towards the right, if you haven't figured it out yet. Yeah, so when it comes to compiler versions, compiler updates are done regularly. And unless there is a very good reason to not upgrade, I would recommend to keep up with the releases. Maybe not pick the latest and greatest, at least follow it closely. Usually it is a very smooth process, but it can be tricky in larger projects where it can expose other instabilities. And collecting good and wholesome data is working smart. All right, and so let's take the first aspect, the build variance. This is usually the first question that we ask our stakeholders when it comes to performance measurements. And the majority of the time, it isn't the answer that we would like to hear. There are more than one aspect that differentiates a release and a debug build. The one that we are interested in is the ndebug aspect. Ndebug is a macro that is used in compilation. It stands for no debug. What it does is in release builds have ndebug defined, which removes the assert. It sounds like an innocent one-liner change with removal of an assert, but it is a conditional statement that behind it. And when you throw in a conditional statement in a loop which is executed multiple times, you do see a big drop in performance. And one other thing is the absence of debug is not the same as the presence of debug. I've fallen prey to this. Like when I look at the compilation line, I see that there's no debug specified, and I think like, oh, this is great. Like it's not a debug build, but your asserts would still be active in that case. So you have to be careful to make sure that you have ndebug specified in your compilation line. All right.
A quick question on that, Felix.
Yes.
And for students as well, please ask questions. But I thought like generally when you're doing the ndebug, I mean, we generally use macros, right? So I'm missing something here when you're, for example, you're talking about the if condition. I just feel like I'm missing something.
Right. So, so when you have an assert, you're essentially doing a check to see if a variable is less than 0 or if it is positive or negative. And that check is a conditional statement.
Yeah.
Right. So let's say you want to check if your shift value is a positive value. So what the way you would do is assert a greater than 0. The a greater than 0 in your it ends up as a comparison statement. It's a conditional statement.
Yeah. No, that makes sense. I guess I'm just kind of thinking about the bigger level, right? I mean, usually wouldn't you say like power behind the macro, and if the macro flag is not set, then the compilers, I mean, it's effectively dead code, right? It wouldn't get into the code. So that's what I'm wondering.
Right. So if you do not have ndebug, then the assert would be valid. If you have ndebug, then it would be replaced by void 0, and the condition statement will not take effect. Your compiler would remove it as dead code.
Yeah. Okay. Thanks. Yeah, and that clarifies it for me.
Cool. I've used the percent detect model here as an example to go through the different optimizations. And these are the different parameters that I've used. I've used this board, which is this ST nuclear board, an ARM embed enabled one. And I've used the GCC toolchain 9.3, and I've used the example percent detect from the benchmarking API that you have in TensorFlow Lite micro. So this is the default setup. And if there is any deviation to it, that would be specified in the slides. And the default optimization that I've used is fast as well. So now let's go on to some measurements. So this is the person-detect model using TensorFlow Lite micro reference kernels. The first build was a release build with Debug, and the second was a default build, which is the Debug build. And you can see that there is a 4x difference in performance. And that is the kind of performance that you would expect from optimized library. And the reason why you have this performance drop is that the core loops of operators like convolution and depthwise convolution have asserts or aborts which are protected by Debug. And in the case of person-detect model, we're talking about where 7 million max in total. So if you add any additional statements that you place in the code loop, which is run almost for every Mac, you see a significant drop in performance. So now if we done the same, if we replace the reference kernels with the CMSIS-NN, then this is how it looks like. There is a small difference in cycles, but if you express it as inferences per second, it's not significant enough to be noticeable. And the reason for that is by design, the code path for the operator is the same for both builds. Now, if you were to just compare the debug builds of the reference kernels with the debug of CMSIS kernels, you'll see that the performance uplift is 15x. Now, as awesome as that sounds, it is quite misleading as well, as that is not a fair comparison to make. If you were to compare results, then you would have to compare the release version with the release version, and in which case it is a more reasonable 4x improvement. So if you see such a boost, at least on a Cortex-M4 or M7, I would question the non-optimized library setup to see if there are any flags that are missing. Now, let's take a case where the CMSIS-NN doesn't do well. This started off with the ticket in TensorFlow's GitHub titled CMSIS-NN kernel is lower than C reference kernel. I don't know about you, but that is something that is not good publicity. So we investigated that, and it turned out that it was related to a compiler option called fno built-in. Now, for the person-detect model, with fno built-in enabled, the performance drops to 3.6 inferences per second, which is just on par with, which is just slightly better with compared to the reference kernels. And depending on your board, you might get a lower performance than the reference kernels. What this fno built-in does is it disables standard library optimizations. And CMSIS-NN uses memcopy for its image to column methods and also to read 4 bytes at a time. And reference kernels aren't affected by this. So what I'm trying to say here is you can expect more such factors in large projects comprising of sub-projects over which you do not have control over. Next, let's take the case of compiler optimization level. I've run the person-detect model over 3 different optimization levels. First, for the reference kernels. The OFAST and O3 are tuned for performance, whereas OS, or optimization for size, is tuned to keep your binary size small. And you can see that it is a considerable impact on the performance. And the choice that you do here is based on your project needs. Maybe you're working on a board that is really low on memory, and you are willing to compromise performance for binary size, in which case it's totally fine to use optimize for size. Otherwise, you know that you can get better performance using O3 or OFAST. Now, running the same experiment on CMSIS-NN, you see a difference for optimize for size, but it is not a dramatic difference. But the thing is, like, it can't be guaranteed either. And CMSIS-NN uses SIMD intrinsics. So at least you would get the SIMD benefits out of the functions. But we do have a combination of functions which do not use SIMD functions as intrinsics as well. So the optimization level is something that you need to be aware of and know that it can make an impact in your project. Any questions so far?
Did everyone follow the SIMD part? Everyone's good? I should totally have a quiz question on like whether there's, if you know what SIMD really is about.
You could have a poll.
Just for, because I know like some students don't necessarily focus on architecture background. SIMD is basically, think of it as like, you know, you've got a vector and a single instruction is then capable of doing an addition on a multiple values all at the same time. So in effect, you're doing one instruction rather than doing like 4 instructions or something like that, right? So, and SIMD width can vary quite a bit. It just depends on the architecture. I don't know what the SIMD width is. It's 128 bits, I assume, Felix.
For the Cortex-M 4 and M7, it's 32 bits.
It's 32 bits, that's it.
32 bits.
Okay, yeah, so it's effectively allowing you to kind of deal with multiple, instead of having multiple instructions, you can use one instruction. This is obviously very dependent on whether the hardware supports it. So that's the simplest explanation.
So what we have done so far is set up a good foundation for data, and we know that we would like to optimize. And this section is about getting a direction to that optimization effort before we actually start optimization. So what I've done here is I've done a layer-wise profiling instead of a complete network profiling. And then I've summed the total cycles consumed by the different operators. So we see that convolution takes up majority of the cycles and followed by depthwise convolution. And that accounts for 99.96 of the total cycles. So this allows you to make a choice to ignore the 3 other operators that you have. And if you dig a bit further into the individual parameters of these 2 operators of conv and depthwise, and sort them out in terms of the kernel shape and the number of, and the depth multiplier and dilation, you can see if you start with depthwise convolution, you have 13 layers which have 3 by 3 kernels with the depth multiplier of 1, and you have 1 layer which has a depth multiplier of 8. So that is fine. And then you move on to convolution, and you see that all the layers, 14 in total, have 1 by 1 convolutions. So this gives us a direction that trying to optimize convolution here would give you the most value for money here. So the next step is to put on an optimizer hat. And the idea here is to get the best performance from your target hardware. So how do you do that? First, it is important to understand your processor's capability and how you're utilizing that capability. And next, you get into the details where you try to figure out the number of general purpose and vector registers that your processor has to decide on the level of unrolling. And it is also good to know your hardware capability in terms of read-write speed. Do you have a cache, or do you have a cache combined with a prefetcher, and all those details. So in our teams here, we use a term called speed of light. So which is defined as the best case cycles for execution of a given arithmetic operator. The best case here refers to the fact that the operators are placed in a fast memory, like tightly coupled memory or TCM. And in the case, for a case of multiply accumulate, which is very common in networks, the ideal sequence that we would like is load followed by multiply accumulate, followed by load, followed by mac, and so on and so on, until you finally store the result of your mac operation. And for Cortex-M 4, the best case is 1 mac per cycle. For Cortex-M 7, it is 2. And for the latest vector-capable Cortex-M 55, you can do 8 macs per cycle. So now that you know the total max of your network and you have estimated how many cycles those max have taken, you can find the processor utilization numbers, and that'll let you guide your optimization efforts. So first, I've taken this for the reference kernels. And this is the diagram that we saw earlier. So where we have majority of the cycles come from convolution and the rest from depthwise convolution. Now, if you look at how many MAC operations that convolution brings compared to depthwise convolution, you will see that convolution brings in around 87% of the total MACs in the network. This gives us an indication that the processor utilization for depthwise convolution isn't as good as the processor utilization for convolution. So that is the first takeaway that we have here. Now, let's determine the processor utilization. So for a depthwise convolution, it lands at 1.7%. And for convolution, it's at around close to 7. It is a bit dramatic, but it is an unfair representation as well, as convolution and depthwise convolution do way more than just max. But if the main takeaway here is that there is a scope for improvement. So to make sense of this processor utilization numbers that we saw, we do two kinds of analysis. The first one is a memory bound analysis, where we've tried to figure out the effective bandwidth that we have used, which is the actual data transfer rate for an operation. And the main thing to understand here is that different memory blocks are involved. Your filters, for example, are stored on a flash, whereas your input and output tensors, they will be stored on an on-chip memory, and which would have a faster access. And often it is about reducing the effective bandwidth, but just the memory analysis doesn't give you a full picture. For that, we turn into cycle or compute bound analysis, which complements memory bound analysis to give a fuller picture. You can think of this as the ability of the algorithm to utilize the processor's capability. And if you want to think about the real world scenario, it is the relation between a supply chain and a manufacturing plant. You want your supply chain to bring in raw materials as fast as your manufacturing plant can consume it. And you want to do it with the least amount of trips as well. And optimization is about striking a balance between the two. So now that we have the data, we can go into the different optimization techniques. Are there any questions at this point?
Looks like we're good.
We're good. All right. So here I've combined the model optimization segment as well. And here, what I'll be trying to discuss is the parameters that underutilize the CPU. And the reason why I want to discuss in this forum is, as future model developers, it gives you the ability to understand what model parameters utilize the target hardware's design best and allows you to design in such a way. So we are going to go through optimization methods wrapped around neural network use cases. And so basically we will take different use cases and discuss one or two optimization techniques around that. The methods as such are generic and can be applied to optimizations in general and in other neural network operators as well. So let's take the case of fully connected. This is my second favorite operator what you have is a vector of n bytes, and its location in memory is like you see in the right-hand side. It's nothing strange about it. And you have n bytes of filters, which produces one output, and that is in a different memory location. And your second output is produced by a second set of n filter bytes, whose location follows right after the end of the first one. The takeaway here is that the input and weights are contiguous in memory, and the MAC operation that you do has a one-to-one mapping to the layout in memory. So no rearrangement of data is required, and you have your ducks in a row. That is one of the base optimization technique that we try to come back to have things perfectly lined up. And then you have the rest of the data as well. So now let's take this use case and see how we go about optimizing it. First, let's work on the memory bound aspect. So this is a very simplified representation of how the code loop would look like. You have an input and you add an offset to it, and you do a MAC operation with the filter along with its filter offset. Now, the common part here is your input vector. So what you can do is you can unroll your filter on the filter dimension so that you read one input and process two outputs at the same time. So essentially what you have done is you halved the number of input reads. Now that in itself is a very good optimization. And reducing memory reads and reusing is a vital aspect of optimization. So you could have a brilliant question here and say, hey, why don't I unroll it all the way if it is as simple as this? Like, why not unroll it 6 times or why not unroll it 7 times? Well, there are limits to effective unrolling. And this is where the number of general purpose register and vector register that are available comes into picture. So let's take this unrolled loop that we saw in the previous slide, and let's try to map the arguments that you see here into the registers that the processor has available. And this is a paper and pen exercise. So first, you have 3 address pointers, and let's assign 3 registers to that. And then you have 3 values, which you read from those 3 addresses. So let's assign 3 more registers for that. You have 2 outputs, sum 0 and sum 1, and those go into 2 registers. You have your input and filter offset. Those are 2 registers. And you have a software loop count. That's 1 register. And ARM Cortex-M 4 or M7 has 13 general purpose registers, and that leaves us with 2 unused registers. Now, this looks like a good match. And the guideline here is to unroll your loops to a point where there are no register spills or reloads. It's not a rule, but it is a guideline to unroll until there are no spills or reloads. Now, let's take a look at the generated compiler output to see if it matches our expectation. So the figure that you see on the top is a snippet from CMSIS-NN for fully connected operator. And unrolling is done twice, like we saw in the previous pseudocode. And the figure at the bottom is the generated assembly code. And you can see that you have 3 load single byte instructions. The LDR-SB is load single byte. So you have 3 of those corresponding to 2 filter and 1 input byte read. You have 3 add instructions corresponding to 3 additions of the offsets. And you have 2 multiply accumulate instructions. So that looks good. That is kind of how you would, if you had just written an assembly, that is how it would look like. And there's nothing strange about it. And the hidden benefit, which is the most important here, is the pre and post increment of pointers are done along with the load instruction. You see the #1 along with the load instruction. That is an indication of post increment. And we're able to do that because your data is contiguous in memory and you increment it by a constant, saying +1, my pointer +1 or pointer +4. So that is a constant increment, and that is why you're able to increment the pointer with the load instruction. Now, had it not been the case, had it been like pointer +n, then you would have needed an additional register to store that offset, and you would have needed an additional instruction to do the increment, because increment with a variable is not supported in the instruction set. So that would have meant 3 additional instructions in this inner loop. Say if this loop is run 1 or 2 million times, those 3 additional million times is a performance drop that you will notice. So now I went ahead and tried to unroll it 4 times now to see if it is still possible to do it without any performance penalty. And you see 4 multiply accumulates, and the load single bytes and add, they all look straightforward. But towards the end, you see that there is a load which is done from the stack. Now that is your register reload. That is your compiler telling you, and now I'm out of general purpose registers. So now I have to reuse a register to go about with the operations. Now, this is an indication that we are around a point where unrolling might not give a benefit. It's not to say that you shouldn't have it like this, but this is the point where I would stop and try ±1 and see if it can be done. So in this case, you could say that this current code from CMSIS-NN can be unrolled can be unrolled one more time, and it would still have been fine. So that is something that we can do. So what we have done so far is in 2 aspects. First, we have tried to reduce the relevant memory accesses while staying within the general purpose or vector register constraint. And the second aspect is to keep it simple, stupid optimizations, where we look for a constant pointer increment in the code loops. All right. Any questions before we move on to the next use case?
Any questions?
All right. So let's move on to the use case of one-by-one convolutions. This is my favorite operator when it comes to convolutions, when it comes to optimization. So when it comes to the memory layout of the input and the filters, it looks very similar to the fully connected operator. So you have your column of input, and you have your multiple rows of the filter, and you perform MAC in the same order in which they are stored in memory. The only difference is you have multiple columns as well. So the one difference, so we would start off with the same optimizations that we did in fully connected, but with the one difference that we would try to reduce the number of filter reads and not the input reads. And the reason for that is your filter is usually stored in flash, which is a slower memory access compared to your on-chip memory access. So that, apart from that, the optimization principles would be the same that we did in fully connected. So now on top of that, let's add a single instruction multiple data optimization. Single instruction multiple data, as Vijay explained earlier, is where you have one instruction, but which operates on multiple data at the same time. So it is more or less, it's like a 2-for-1 or 4-for-1 offer. And let's take the case of a multiply accumulate and see how it works out here. So the 2 boxes that you see with DSP extension and MVE extensions are a very simple case of load and a multiply accumulate operation using a SIMD instruction. So previously we saw that we did multiply accumulate using an MLA instruction, whereas SMLAD for DSP extension is the SIMD instruction that does 2 MAC operations in one instruction. And you can see the #4, in front of the load instruction. So that again is constant pointer offset, which is what we really want. And yeah, and the thing is like it handles even number of MAC operations. And if you have a MAC operation which has a tail, which is which has odd number of operations, then you would need to handle that separately. And that is usually not very effective. Whereas if you take the MBE extension or the vector extension that you have for the latest Cortex-M 55 processor, you do a vector load and a vector multiply accumulate instead. And this instruction operates on 16 MAC operands, even though it does just 8 MACs per cycle. And additionally, you have something called as tail predicated loops, which handle both even and odd elements in the same loop. It is still inefficient to have odd number of MAC operations which do not fit into the maximum number of MAC operations that your processor can do. But at least from a coding point of view, it looks cleaner. So now we have applied SIMD or SIMD instruction, SIMD optimization to the one-by-one convolution. And if we apply further simplification to the code loop, what you can do is like you can move the handling of the input and filter offset outside the code loop. So what you're trying to do is you reduce the number of loads and also you free up registers that can be used for deeper unrolling. I've given a reference here and very details on like how you can do that, how you can move the handling of the offset outside the code loop. And this is something which we do in CMSIS-NN. So to recap, on top of what we have done for fully connected, we have on the keep it simple stupid optimizations, we have simplified the code loop even further by moving out the input and filter offset adjustments. And we have added single instruction multiple data optimizations to better utilize the processor's capability. All right. So now we move on to the next use case, which is convolution. Convolution is where the most common technique, image to column, is supplied. And the reason for that, the reason why we do this is the input elements aren't contiguous in memory for a given kernel shape. So if you take the figure on the top right, the elements 1 and 2 are next to each other in memory, but 3 and 4 aren't. So how this ends up, like when you actually write the code for this, is it is a conditional statement where you have to check if you have reached the end of the column for the first row. And then you need to add an offset, which is not a point, which is not a constant. That is basically everything that we have tried to avoid so far. So that is where image to column technique comes to the rescue. What we do here is like we just extract out the input tensor elements and place them contiguous in memory. Very similar to how things were already arranged for fully connected or one-by-one convolutions. And the thing is like it requires an additional memory or a scratch buffer to operate. If you were operating on a cloud, you would probably do this image to column transformation on the complete input, and that would be fine. But on a Cortex-M or the embed on a TinyML scenario, we just operate on 2 segments at a time. So we just unroll 2 columns at a time. And there is a reason on why we do 2. One, of course, like we would like to keep the memory requirements low for the additional scratch buffer. And also it is the point at which the register utilization is max. Like if we had 3 or 4 columns unrolled, then it would have resulted in register spills and reloads, and we might not get as many. We might not get the benefit that we might think that we would get there. So by now, like you would you'd start seeing a pattern that we do when it comes to optimizations. We keep coming back to the same basic principles in different ways. So now, as awesome as image to column is, it takes cycles to rearrange data, and it requires an additional scratch buffer, which is a premium in TinyML scenario. So personally, I believe that if 1/n convolution can do the job, your image to column step can be avoided while still retaining the benefit of it. So what a 1/n filter is that it just has one row, so that your data is already contiguous. So you don't have to do any rearrangements. Just think of it as an expanded use case of the 1/1 convolution. And right now, we do not have any models in the embedded space with 1/n filters, or at least popular models with 1/n filters. And this is where model design can play a role in end optimization. The problem that I described here is not typical to ARM processors. It is a generic problem. So if we have models in future in the embedded space with 1/n filters, then I think that we can make use of, that would be a very good optimization in itself. And we can add optimizations in CMSIS-NN for that as well. Right? So, and so far, we have, on top of what we have discussed so far, we have added image to column techniques for contiguous memory access. And we have discussed about how 1/n convolution can let you eat your cake and have it as well. Any questions at this point? So next, let's go on to depthwise convolution. This is my least favorite operator, as it's one of those operators where you just don't get any. It just trashes processor utilization numbers. And depthwise convolution followed by 1/1 convolution is a quite popular building block in modeling world for obvious reasons. It is less MAC intense, and who doesn't like less MACs, right? But what you gain in MACs, you lose in inefficient memory accesses. The accesses are non-contiguous, and you don't have fixed offsets for memory increments. And that is, again, everything that we have tried to avoid so far. And depthwise convolution was the first kernel that I optimized in CMSIS. I've spent many frustrating days on it. I applied all of the techniques that we discussed so far. And while it was an improvement, it wasn't anything worth bragging about. And after a while, we had a second pass at optimization, and my colleague tried this time. And he removed the SIMD optimization and the image to column method, and was able to get a considerable improvement. At least that was a good lesson for me, to not just tick boxes. And whereas in the case of Cortex-M 55, we still have SIMD, where we still have image to column and SIMD methods used for depthwise convolution, and that is still better. So, and also, for example, a 3x3 filter translates to 9 elements on which you do a MAC before you requantize it and store the results. That you basically end your MAC process before you even start it. Let's put it in that way. If you take a convolution operation, you would do your MAC on maybe 128 times or 256 times, depending on the number of channels. So, but all said, it has a place in model design for what it brings to the table. That is minimized number of MACs. So there is one other thing that I would like to discuss in terms of model parameters that aren't.
Felix, sorry, just to give you a heads up, 10 more minutes.
Yep, sure. One other thing that I would like to discuss is the inefficiencies of the first layer. This is if you take the first layer, it usually has one channel or 3 channels, because that is your typical input. And if you take the person detect model, for example, you have depthwise convolution applied. And in this case, like, you could actually apply a convolution operation instead, because it's just one layer of input. So I went ahead and tried convolution, tried convolution on using CMSIS-NN. First by using the default kernels, and then by using the image to column kernels. It fared way worse than a depthwise convolution did. So what I'm trying to say here is, in this case, it was a very good choice to go for depthwise convolution. And that is something that you might want to keep track as well. So any channels, when you have channels less than 4, it is quite inefficient. It is, if you use a generic convolution or depthwise convolution functions, it would read 1 byte at a time. And that is like running a flight with 25% of filled seats. No matter how you code it, it is inefficient. But it's one of those things, like, it's how it is. And I just wanted to bring it up to say how the first layer is usually different in terms of processor utilization compared to the other layers. So now we come to the final part of the operators, pooling. And this is where we start rehashing all the techniques that we have learned so far. So when it comes to max pooling, at least Cortex-M 4 and M7 doesn't provide any SIMD instructions. So what you try to do is you try to optimize your memory reads, and you read 4 bytes at a time. The commented out section, the section with red comment that you see there. And once you have 4 bytes of data in a register, general purpose register, you process from that. So in that way, you process data from the fastest memory possible, which is register space. If you take the Cortex-M 55 with vector extension, there we have SIMD instructions, and it allows you to perform max operations on 16 bytes in one instruction. So with all this done, how does the processor utilization look post-optimization? So this is the result of processor utilization with CMSIS-NN kernels. And you see that it's an approximately 4x improvement. I know it isn't 60 or 70% that you might have hoped for, but the reason for that is your operators do many more things than just a MAC operation. So you have requantization, which takes a significant amount of time. And then you have your input or filter offset handling, and you have your memory access delays, as not all memory accesses take 1 byte. And you have padding and stride on top of that. So that is basically how it looks like at the end. And that brings us to the end of our presentation as well. I have some references here, and here I have the instructions and instructions that I used to create all the that I used to generate all the numbers in this presentation. I still have to upload the patch for the micro benchmarking APIs. I made some small changes to that to get these numbers. I'll upload that, and I'll provide these slides again to Vijay. Any questions now that you've seen the whole thing?
Thank you, Felix. Do students have questions?